My TTL Computer. This is an overview of revision 4 of my TTL Computer. And just a quick review. We started out with revision 1 as basically the Ben Eater design, accessing only 16 bytes of memory. Revision 2 expanded to an 8-bit program counter and 2-byte instruction word and accessing 256 bytes. And revision 3 basically added the UART and terminal capability and introduced the hex loader and being able to load remotely developed programs onto my TTL computer by the serial line and the hex loader. And revision 4 brings us to pretty much completion on this hardware and gives us full access to the 2K of memory that's on board. And I left you with a riddle last time that said that I've achieved the 2K access by only moving 3 wires. And I left you with the quandary of what my solution was for that. And we're going to take a look at that briefly today. And we'll also take a look at the basic capabilities of the end result. And then at subsequent videos, we'll take a deeper dive into some of the complexities of the solution that the software and the firmware and the microcode had to overcome to implement revision 4. So we basically are at a lot of limits that we're hitting, even at revision 3. So we're pretty much out of breadboard space. Almost all of our chips, virtually all of our chips, and the important chips like the control unit and the UART and the ALU and our output display chips, all of the pins are used. We really have no place left for expansion. So our natural progression to get to access 2K would be to increase the program counter and increase the memory address registers. But I said we're at our limits, and we really couldn't go that direction. So what did I do? I said that we were only going to move 3 wires to achieve going from 256 bytes to 2K. So we had some vestigial organs, if you will, left over from our evolution from a 1-byte instruction word and a 4-bit memory address up until where we are now with 2-byte instruction words and an 8-bit address. And if you remember all the way back in the beginning and with the Ben Eater solution, with the 1-byte instruction word, we had the upper 4 bits being the opcode and the lower 4 bits being the data or the memory address. And we didn't change that when we went to an 8-bit program counter. We're not using these lower 4 bits anymore because we haven't added a second byte that has our memory address. So we have these 4 bits at the lower end of our opcode, if you will. These lower 4 bits that are just not being used, and they're also being carried through to the instruction register. We have the same 4 bits not being used. So what I decided to do is we're using, and these we need 3 extra bits, right? We're at using an 8-bit program counter, an 8-bit memory address register. We need 3 more bits to access 2K, and conveniently, those 3 bits are not being used, and they're not being used in the opcode. So what we're going to do, and what we have done actually, is we've taken those lower 3 bits, and we've moved those wires from the instruction register up to the topmost bits in our static RAM chip. So now, to fully specify a memory location in the 2K address space takes our 8-bit program counter plus the 3 bits from our opcode, the lowest 3 bits from our opcode, from the instruction register. Those together will allow us to access, to fully address a byte in the 2K memory space. And that's exactly what we're going to do. And that in fact is our solution. And the extra button that I made reference to is a button just so that we can zero out and even load data into the instruction register. We haven't been able to do that prior to adding this button, because it enables the write into the instruction register. So that's our solution, and it's almost not worth discussing at the hardware level. Because all we did was we moved those 3 wires, the lowest 3 bits from the instruction register to the RAM chip. And really, PS, we're done with our revision for hardware changes. Now, I have a program running that is demonstrating accessing the 2K address space. So let's back up one step. So what we kind of have implemented a bank switching here, right? So we've gone from having just a single bank, right? We weren't without using the bits in the instruction register. We just have we have one bank of 256 bytes, bank 0, if you will. Now, if we set the first bit in our instruction register, now we're going to be at bank 1. If we set the second bit, we'll be in bank. We'd be in bank 2, and that's exactly how we would access the rest of the address space. So I have just a simple program running now that is all it's doing is starting out in bank 1, which is memory address hex 100. Starting out in bank 1, it's outputting a 1 to the display, and then it's jumping to address 200, and that means that we would see the 2 light up in the instruction register. Then it's outputting a 2 to display. Then it's jumping to bank 3, which is address 300, and it's outputting 3 to the display, and it's doing that all the way up to the bank 7, and then jumping back to memory address 100, which is bank 1. And we can just see that we kind of see that counting progression in our instruction register, right? We have 3, bank 4, bank 5, and then we'll see a 5 over here, and then bank 6, and then we'll see the 6 over here. Right, and we're seeing the switch in the bank first because it has to jump to the bank, and then it has to do load an immediate instruction for the value that we're going to display, and then it outputs that to the display. So we see the instruction register being set, which is the bank, before the display updates, right? And that's it. We're only running at 2 hertz now, so it's really slow, just so we can see what's going on. So that's it in a nutshell. Things running, and this is just showing you, just giving us a way to see how we're cycling through the different banks using the instruction register. So I kind of haven't told you how that works, but and we're not going to really dive into that too much in this overview video. We'll talk about the details of that in our next video, because all the work for this revision 4, you see how simple and trivial it was to do the hardware changes. All of the fancy work that had to be done to make this this solution work and be pretty seamless from the programmer's perspective is are the significant changes that was been made in the microcode, in the firmware changes, and also in the assembler and our 8-bit transfer program and the hex loader are really doing all the heavy lifting for us to make this the use of the hardware and accessing the full 2K to be pretty transparent to the programmer. All right, so this again was just a little demonstration to just kind of really emphasize showing you how the bank switching, if you will, is occurring here, or the bits being set for the banks, and we're running here at 550 hertz right now. So we can just see that we're accessing, all of the banks here, all the memory banks. Okay, then in our next video, we will take a look at the significant changes that have occurred on the firmware and the software side of my TTL computer, and from the programmer and the end user perspective, it seems really functioning as a different computer now. And we'll see that in our next video. And that's it. Thanks for watching.